Okay, and we are back. So the question before the break was, what happened with the inverse of a matrix, here 2 by 2, when the determinant is 0? So if you don't remember, a 2 by 2 matrix can be written in general form as A, B, C, D. And in the break, I quickly did this with SymPy. So I've here defined the symbols A, B, C, and D. I use SymPy matrix. I provide a nested list 2 by 2 with the coefficients A, B, C, and D. I store the result in M1, matrix 1. And I ask Python, hey, what is M1? And I see it's a matrix A, B, C, and D. So this is now a SymPy matrix. I then have two other questions to SymPy. What is the inverse of matrix M1? And what is the determinant? And when you pay close attention, you actually see that in each element of my matrix is written 1 divided by the determinant here, AD minus BC. And we have this in each of the elements here. Now going back to my questions before the break, what happens if the determinant is 0? Well, if AD minus BC is 0, then 1 divided by the determinant is infinity, right? So what we have written here is D minus B minus CA times infinity. Right, and this is basically what is the matrix where the elements are infinity? So this is then not usable anymore. So our singular matrix, a square matrix whose determinant is 0, has no solution here. So we can check if our matrix has, or our system of equations in matrix form, having a solution or no solution by checking the value of the determinant. If the determinant is 0, we will not get a solution because the inverse of our matrix will be infinity. Yeah, or better to say it's not defined, right? Good. Now, we already had encountered in NumPy how to determine the inverse of a matrix. We do this by calling the sub-package linear algebra and then the method inverse, inv. So, shall we check what we get when we have a singular matrix? So in a singular matrix, AD must be equal the opposite of BC, right? So we could have 1 and 2 on the diagonal, and then the off diagonal has minus 2 and 1. So far, so good? Do you follow? Yes, no, maybe? We can always split the cell. Sorry, this is here, right? No. What did I do? There we go. So looking at the matrix, so 1 times 2 is 2, minus 2 times 1 should be this one here, right? 1, 2, minus 2, 1, yes, like this. So NumPy, tell me what is the inverse here? And again, this is a singular matrix, already see the vectors are linearly dependent. And it will also tell me, hey, you have a singular matrix. What you asked me to do, the inverse here, is not possible. So good? Okay. So there are other methods available as well. And today I want to introduce the one in SciPy to you. So SciPy is a package that is built on top of Python. It's for scientific computing. There we go. The documentation is available at this website, scipy.org. They have a lot of examples. It's a really, really good package, not only for solving equations, but also for fitting, regression, interpolation, extrapolation, triangulation. It's just so much, right? And whatever numerical problem you have, it's always good to have a quick look into SciPy just to see if there is a function implemented already that you can use. So the considerations we have to do is now see when do we actually have access to a solution, because we know how to get an inverse in NumPy. I will show you later how to get an inverse in SciPy. And I already sneaked in how to get an inverse with SymPy to solve your equations. So you have 3 different possibilities already, right? Well, 2.5, let's say. And the question we always have now is, can we form the inverse of our matrix A? Because if we cannot get the solution, right? So the matrix must be non-singular to get the inverse, right? And the matrix A is singular if the rank of a matrix is less than n, or the determinant is 0. Right. So if the determinant is 0, we can just change here a value a little bit, right? 2.0000000000000000001. Determinant is not 0 anymore, right? Numerics, right? How accurate are the numbers we actually store in NumPy? In NumPy, we cut off after digit 16, right? Rounding errors. We can make it a little bit larger. Try again. But then we get like crazy numbers here, right? E to the power of 14, where our linear coefficients are 1 and 2. Plus, if we change the numbers a little bit, now try to remember these numbers here, right? Do they change a lot or do they change just a little? They change a lot. So just now it was here 10 to the power of 14. Now I just removed a few zeros here, right? Now it is 10 to the power of 12. So from 14 to 12, that's like 3 orders of magnitude. Right. So whatever algorithm NumPy is using to determine the determinant, to find then the solution of this determinant, is subject to numerical stability. So how small perturbations actually affect the solution. Ideally, small changes do not impact the accuracy of your solution. But this is not always given. So what we will do is to analyze if our system of equation, given in matrix form, is prone to be or drawn to be impacted by numerical noise. So we're going to check if our system is well conditioned. So to be well conditioned, we define a condition number that should be close to 1. So if the condition number is 1, it's good. If it's very large, it's not good. So how can we then define a measure of this condition? Well, looking at the problem we have at hand, that is ax equal b, we consider small changes to this problem. So this is ax, right? And now we perturb x a little bit, plus delta x. And note that x is much larger than delta x, or the opposite. Delta x is much smaller than x. So x could be 1, and delta x could be 1 over 1 million. Okay? If x is 1, delta x cannot be 1. That is too big. So what we want to see is, now what is the impact on our vector b? Right? So we are still in a linear region. So in the simplest case, a is just one number, right? Let's say 1. X is 1. Then b should be 1. Now if we add a small number to x, let's say 0.5, then we can take apart, right, expand this product, and then we see a delta x equals delta b. X is 1, sorry, a is 1, x is 0. Delta x is 0.5, then delta b should be 0.5 as well. It turns out, however, that if the condition number is not close to 1, this relation is not true anymore. So what did we do? We are going to compare the relative size of our solution to the small change. That would be delta x divided by x, and small changes in b that are delta b over b. So the magic is happening here in this line. Right? It fits all in one line. So how do we read this? Well, we start with delta x divided by x. Note that here are absolute values, so we don't have to distinguish between plus and minus. Now, delta x should be equal a inverse times delta b. Do you know why? Well, because we are still having a linear theory here, right? So we just can say a times delta x equal delta b. If we multiply this with the left, with the inverse of a, then we get delta x equals a minus 1, right? Inverse of a times delta b. So far, so good. Shall I do this on the here? You? Okay, you can follow. Very good. Right. So there is a relation where I can take the absolute value of a product and say this is smaller equal the absolute values of the separate factors taking as a product. Right? Ideally, it's the same. Basically, the vectors pointing in the same direction, but there could be slightly off, right? Okay, so we have a smaller equal inverse of A. Here we have now the norm, right? Because it's a matrix in general, and then we have here the norm of this vector, and that is equal A inverse norm times B times B delta B divided by B. So where is the B coming from? If we multiply B divided by B, so 1 over here, then we get 1B in, and we just reorder the B. We basically swap these two B's here. Reorder. But then we know A minus B, this one is smaller equal X, right? Yes, no, maybe? And then we have X divided by X, so X cancels out. Still okay? Can you see? No? Okay. There's a question. So we are here. A minus times B divided by X. So we have the norm of A minus times B divided by X. right? But A minus times B is just what we had over here. So when we have AXB, so with AX equal B multiplied with the left from A minus, we get A minus times A, which will be 1 times X equal, A minus times B, right? So far so good. So we get X equal A minus times B. But now we can say we take the norm of this vector, the norm of the product, but the norm of the product should be smaller equal the product of the norms. So far so good? Right? Okay, so this is where we get the X in. So over here we then write just smaller equal X divided by X, which is 1. So far so good? Okay, so we go down here again. Right, and then we're left with A minus times A, which together, right, ideally should be 1. But, right, so the product of the norms is still different than the norm of the product. So when this number here will be equal to 1, then the changes here and here should be similar. But if this is very, very different, for example, this is 1 and this is infinity, but then it will be much larger, right? And then the changes in x are much larger than the changes in y, and our solver will have great issues to reliably incorporate these small changes. So this is already the condition we are looking for. So we basically now use the definition that the condition number A equals the product of the norm of A times the norm of the inverse of A. So far, so good? Okay, few examples. So we have here now a matrix A and a vector B defined, right? So our matrix A is 2, 3, 5, 4. The vector B is 4, 3. With this, in principle, I can now set up a system of equation, right? Where I would first check the rank, right? It's a quadratic equation, rank is 2. I'm interested in the inverse of A, right? I could check if the determinant of A is 0, then I can stop here. Next thing I need to check is what is the condition number. To check the condition number, I'm going to use the COND method. So basically the condition method here. I pass A as an argument. On the value I get back, last time it was 7 point something. Now the way the condition number is actually computed can differ depending on the methods used. So 7.58, is this good? Is this bad? I think it's still okay. What we can do is to confirm the condition number by computing the norm of A minus 1 times the norm of A individually. So what I have done here is I compute the norm of A, right? I compute the inverse of A, and then I take this as a norm, and I take the product of both. So note that the norm of a vector is a scalar, of a vector, and the matrix is a scalar. So I can work here with a vector multiplication. What we observe already is a small difference between NumPy's condition number and our self-written condition number. Okay, so now we have a number of 7. What we don't have is yet a solution. Right? And we don't have an estimate, well, we don't have experience to tell us condition number of 7, is this now larger than 1? Is this too large? Do I still get a reliable solution? So what we need to do next is to see well, what happens if we change the matrix a little bit? What condition numbers could we get? And then when we have these two different condition numbers, right, 7 and some other value, could be larger or smaller, do we still get a reliable solution? So I set up here a second matrix, 2, 3, 5.999, and 9.00001, right? When you have these vectors here in that matrix, you should observe that they are almost linearly dependent. Meaning I can take one vector, multiply it by 3, and I get the other vector. Right? And the differences are here in the 100 of 1 over 100,000. So I have defined this vector, I get the condition number, and I get what? 4,062,000, right? So this is much larger than the previous condition number. In an earlier example, we already saw that when I push a little bit harder towards linear dependency, meaning I make it linearly dependent, then I run into trouble getting the right condition number, and the inverse, right, the determinant and the inverse spikes to infinity. So this right, numerically basically reaches here infinity. So there's a, I'll change this back. Yes, so reaching values of 4 million, yes, this is large. Plus it will affect how we compute the inverse, and what you can play around with these numbers here a little bit, change them just a tiny bit, and the impact on the inverse should be quite severe. Right, so small changes in A give you large changes in the inverse. Right, and will basically translate it into small changes in B will give you large changes in X. So how do we analyze this with more rigor? We already saw that the issue actually becomes more severe when or if we see linear dependence in the vectors constituting to the matrix. Now we are using SymPy, and I already showed you how to make a matrix in SymPy. Now, to make a matrix, to make vectors in a matrix linear dependent, I just need to have the same numbers in the rows, right? To be able to diverge from this linear dependence, we're introducing a parameter p. And obviously, if we have plus or minus p, that could be one way. But here we follow the course book. The course book mentioned square root of p and 1 over the square root of p. So square root already implies that our values of p should be positive. If p is very large, the two vectors will be very, very different. right? The square root of 1,000, let's say 10,000, and 1 over square root 10,000 will give you quite different numbers, like 100 and 1 over 100. Okay, but so the matrix A is basically now a function in matrix form. Our matrix vector B is 1 and 2, that is fine. And I can use SymPy to solve now matrix A under given coefficients B. Let's do that. Does it work? No, nothing defined. Here we go. So that takes a little bit again. So in the next part, we will convert our analytic solution, right? This is now our analytic solution, to a numerical form. The numerical form we will solve with NumPy. And then we're going to compare the analytic result, the exact one, with the numerical insights. And then any large difference between analytic and numerical will be an error. So luckily, we already know how to combine SymPy with Lambdify to interface with NumPy. Right, so we are forming the solutions, right? We call them solution of X, and then we apply, this is lambda P. Yes, we define a matrix A with NumPy through the lambda keyword, so this is still just pure NumPy here. We introduce a NumPy B vector, and we get the numerical solution by invoking NumPy linear algebra inverse of A for parameter B that is passed to lambda multiplied with a B vector. So far so good. So X equals A minus the inverse of A. This is this part times B. Alternatively, you also can use NumPy linear algebra solve, also works. So you have two options here, either this or solve in NumPy. Now the values for P, we will scan from 0.9 to 1.1. Right? And the critical part is where P equals to 1, because then we have linearly dependent vectors in our matrix A. When we do this, right, we also compute our condition number as a value of P and record the results, one analytic and one numerical. So let's see. So we have basically asked Python for two plots. Then we define values of the array for the p-values from 0.9 to 1.1, 200 different values. We, sorry, need to execute here. Right. So the other parts we're going to use is basically a list comprehension, where we take the symbolic solution, substitute P with a value from the NumPy array, and evaluate the function. So we get a list of values. Right, and if we execute all the parts, so here's the object getting the figure, here's the NumPy array with the p-values, then we ask for all the different solutions analytically and numerically, and we plot with plot labels. So what do we get? We will get plots like this. So on the right, we see the values for P and the calculated condition number. You see it goes all the way up to 8,000. On the left, we see the differences as symbolic result minus numerical result. And right, so if we have a value close to 0, means our numerics and our analytics give us the same values, which is good. That's what we want to have. But the closer we go to a p-value of 1, the larger our condition number is, the larger is the differences in relative values between delta x and delta b, the larger become the changes in our solutions. Between symbolic, the one we trust, and the numerical one. So what we can conclude from here is, well, yes, we need to check the condition number. We know that larger values lead to larger differences between the real solution and the numerical solution, and that values probably in the region of 1,000 or more of the condition number lead to noticeable changes. So the value of 7 we saw earlier, that's not reason to concern. But if you see like 4 million or 3,000, then we need to be very, very careful. Okay, questions so far? If not, then we still have 15 minutes. I'm not going to do something new today in like 15 minutes. So next time we continue with linear systems and SciPy. To find the solution, it will talk about lower and upper decomposition of a matrix in lower triangular form and upper triangular form. Right? But if not, then you have 15 minutes to do some exercises. If you have solved them already, there should be NumPy exercises and then maybe some SciPy exercises. And if you have questions, I will be here for the next 15 minutes. And then, so one more time, for those that might have joined late. So final exam, 3rd of June, 9 a.m. on site, location to be announced, closed book format, so nothing you can use but a self-written double-sided A4 paper to help you remember some of the commands. Okay.